So in this last video, we're going to introduce the mean value theorem, prove it, and show some of its applications. The first biggest one is something we've been using. So we've said that if f prime is positive on the interval AB, right? And we've said, oh, well, if it's positive, it's increasing. And so then f of A would have to be strictly less than f of B. And we've been saying this is true because we've interpreted, oh, well, if the derivative is positive, it's increasing. But that's just kind of an interpretation. It's not a definition. It is nothing of that sort. And so how could we get a handle of proving that this is true? And the mean value theorem gives us the mechanisms to do that. So the mean value theorem its hypotheses should strike you to being very similar to Rolle's theorem, which we introduced in the last video. It says, okay, if f is continuous, so it's continuous and it's differentiable. Those are the same two hypotheses from Rolle's theorem. The only thing is missing that we're not going to require that f is equal to itself at the endpoints. So if f is continuous and differentiable, then somewhere on the interval c, there has to be a c so that the derivative is equal to the mean value of the function. So f of b minus f of a over b minus a. Think of this as the slope of maybe the secant line. So again, this is where pictures are quite helpful in explaining what we're talking about. So here's we're going to graph our function between a and b. So say it looks something like that. And if I were to connect my endpoints, so if I were to draw a line, straight line between A and B, so what would the slope of this line be? Well, the slope is the change in y, so f of B minus f of A divided by B minus A. Right? That would be the slope of this line, which is exactly what's on the right-hand side of this equation, the slope of the line that connects the two endpoints. Okay? And then what the mean value theorem says that, well, if I were to move this line around, I could find a place where the slope of the graph, right? What I do, I just took that line, moved it around, and the slope of the graph is identical. And so that's the spot. So if I looked at where this occurs, right, kind of draw a dotted line up, that here, the slope of the graph is the same as the slope of the graph of, or the slope of the secant line, f prime of c. They're equal. So to prove this will require actually Rolle's theorem. If you can imagine in your mind, so let's take this graph, and if we could do some kind of rotation to it and lift it up so that f of a and b were equal, so we're just going to kind of rotate it, then the slope would be 0, and of course that's what Rolle's theorem says. So how do we use that idea to prove this? Well, first off, let's this line can be extended on, right? Can extend out that way and extends this way. And what's the equation of this line? Well, it's y, or I'll call it L of x. I'm going to call it a function. So L of x, the line, is equal to the slope, which is f of b minus f of a over b minus a times x minus a plus f of a. Right? That's just my point slope form of the line. That this line, this blue line here, the secant line, can be given by the slope of that line times x minus a plus the point that's on my line way over here. Well, some things to note about L. First off, what is L prime? Well, it's a line, so L prime of x is f of b minus f of a divided by b minus a. That's its derivative. I mean, that's its slope. So slope is the derivative. Another nice feature about our line, well, L of a. Well, we see it goes through the point f of a. So L of a equals f of a. And you could, also just put it in the equation. Evaluate it. A minus a is 0. Well, we just get f of a. Similarly, L of b is f of b. Again, it goes through that point. At b, the line goes through the point f of b. But again, algebraically, you could put it in here. If you do b minus a, it would cancel there. I get f of b minus f of a plus f of a, which would be f of b. So good. That's some facts we know about it. So we're going to use those facts to build a new function called, I'm going to call it h of x. So I'm going to define h of x to be equal to our original function minus L of x. And this is doing exactly what I was suggesting. If you can picture it, if I do the function f, that's this yellow curve, and I subtract it away from the blue curve, it's like rotating it a little bit so that the endpoints will be equal. So, and I'll show you why. So here's h of x. It's equal to this function. Since f is continuous and L is continuous, then their difference is continuous. So h of x is continuous on the interval AB. Also, f is differentiable and L is a line. It's differentiable. So h of x is differentiable on the open interval. And then the last little bit, that h of a will be equal to f of a minus L of a. But L of a is equal to f of a, and so this is equal to f of a minus f of a, which is 0. And h of b would be f of b minus L of b. But again, L of b we've calculated as f of b, so this is just f of b minus f of b, which is also 0. So we have that h of a is equal to h of b. And these are the three necessary assumptions, requirements for Rolle's theorem. That it's continuous on the closed interval, differentiable on the open interval, and equal on its endpoints. And so by Rolle's theorem, there has to be a c that the derivative is equal to 0. So there's a c so that 0 is equal to h prime of c. Well, okay, what is h prime of c? Well, it is equal to f prime of c minus L prime of c. And L prime, we calculated that up here, is just the slope of the line, f of b minus f of a over b minus a. So that gives me that 0 is equal to f prime of c minus f of b minus f of a all over b minus a, which gives us the end, our solution. Therefore, f prime of c, right? This is exactly what the mean value theorem says should be true, and by a nice intermediate function, we're able to derive this using Rolle's theorem. So, well, how does this tell us that if the derivative is always positive, then f of b has to be less than f of a, right? That's how I started this. I said, well, the mean value theorem can be used to prove this thing that we've been saying on forever, that if it's positive, that we've interpreted this, say, oh, well, if the derivative is, if the function's increasing, then f of a has to be less than f of b. So by the mean value theorem, we're done with the mean value theorem, we've proven it. So now if we said, let's assume that f prime is always positive. But then we know somewhere the derivative is equal to this, but 0 is going to be less than f prime of c, because it's always positive. And that's equal to f of b minus f of a divided by b minus a. Now b minus a is positive, so I can multiply both sides by b minus a, preserve the inequality. So this tells me that 0 is less than f of b minus f of a, which then tells me that f of a has to be less than f of b. So we've just been using a heuristic saying, well, if the derivative is positive, then it's increasing, therefore the one endpoint has to be smaller than the right endpoint. But now the mean value theorem gives us the fundamental truth of why that has to be true. Okay, so what can we do with the mean value theorem? Well, one, we prove this, we can use it to prove this very important fact. So now what we've been doing on intuition, we know is fully grounded in mathematics. The mean value theorem will show up several other places when we look at integrals. Oftentimes, though, problems that are used to just test a student's understanding of the mean value theorem would be find a C in the interval 0, 2 that satisfies the mean value theorem for, say, f of x being equal to square root of, let's say, x plus 1. Okay, so this is not using the mean value theorem, but like I said, it's a common question you'll see on homework or in exams, just to test if a student understands what the mean value theorem is saying. So I've got a function here, f. It is differentiable between 0 and 2, and it exists. It's continuous between 0 and 2. So it meets the definition of the mean value theorem. So there has to be some c, so that f prime of c is equal to f of b, which is 2, minus f of a, which is 0, all over 2 minus 0, or b minus a. Somewhere the derivative has to be equal to this, but in this particular function, what is that? Well, that's the square root of 3 minus 1 divided by 2. So somewhere the derivative has to be equal to this number. And the problem is asking us, well, since it has to be true, do your algebra and find out where it's true. So let's first compute. What is f prime? Well, f prime of x is equal to 1 over 2 square root of x plus 1. Right? That's the derivative here. And so really the problem is now asking us algebraically solve this problem. When is square root of 3 minus 1 over 2 ever equal to 1 over 2 square root of, I'm going to call it a c now, c plus 1. So doing some cross multiplication, this tells me that square root of c plus 1 has to be equal to 1 over root 3 minus 1. Now I need to solve for c, so I'm going to square both sides. So c plus 1 has to be equal to 1 over, what is it going to be, 4 minus 2 root 3. And so c has to be equal to 1 over 4 minus 2 root 3 minus 1. And that's what it's equal to. Now, we can put this in the calculator, and this is approximately 0.4. But that's not necessary. This is just kind of a sanity check. Is that number in our interval? And sure enough, 0.4 is definitely between 0 and 2. So this is the value c that this is the value of c that satisfies the mean value theorem. So another application could be a problem where we have, say, some bounds on our rate. For example, a girl on her bike cannot ride any faster than 5 miles per hour. If she rides for 30 minutes, what is the farthest distance she could travel? So we're going to, let's just set this up and say that d of x, or maybe d of t, is distance traveled. And will be in miles. T is time, and it'll be, since our rate is miles per hour, will be time in hours. And the question is asking, well, she rides for 30 minutes, so that's half an hour. What is the max possible value of d of 1/2? Right? That's what's being asked. And so we can go about solving this problem. Let's just assume that that this distance function is continuous. So we'll just say that d is continuous and differentiable. Even though I don't know what the function is, we're just going to make that a requirement of our distance function. This distance traveled is continuous and it is differentiable. Nowhere do we have, if we graphed it, we wouldn't have any jumps, discontinuities, no sharp corners. So we're assuming that it meets the requirements of the mean value theorem. And we have this fact that d prime, right, the change in distance, which would be her speed, is less than or equal to 5. Right? So her rate of change is in position. That's the distance form is measuring that. So her rate of change is less than or equal to 5. Well, how do we use the mean value theorem for this? Well, the mean value theorem says that somewhere that there is a c that's between 0 and 1/2, where d prime of C is equal to D of 1/2 minus D of 0, all divided by 1/2 minus 0. Well, D of 0, if no time has gone by, she hasn't traveled anything, so D of 0 has to be 0. We don't know what D 1/2 is. That's actually what we're looking for. What's the max value of D 1/2? And so this is 2 times D of 1/2. Okay, so somewhere the derivative is twice whatever the distance is of 1/2. But what do we know about D prime? It can't be any bigger than 5. Even for this value, it can't be any bigger than 5. So I can take these two facts, the fact that D prime isn't any bigger than 5, and that D prime is equal to 2 D 1/2, putting these together, I can state that 5 is bigger than or equal to 2 times D of 1/2. Or solving for D of 1/2, that D of 1/2 has got to be less than or equal to 5 divided by 2, or 2.5 miles. So that is the maximum distance. The maximum distance she could possibly have traveled is 2.5 miles. And it occurs if she, from the very beginning, immediately starts pedaling at 5 miles an hour. Right? We know at the beginning she's not. She's at a rest, more than likely. But at that point, she'll immediately jump up and be pedaling as hard as she can for half an hour, and the farthest she could possibly travel is 2.5 miles. Okay, well, that was a fairly in-depth investigation of some facts we can know about continuous functions. We've got the intermediate value theorem, we've got the Rolle's theorem, and we have the mean value theorem. All these theorems, especially the intermediate value theorem and mean value theorem, are very important. They solidify our intuition about functions that are continuous and differentiable, and allows us to work without any concern that our intuition is supported. So that ends section 3.8, which ends chapter 3. Happy mathing to you, and good luck with your studies.